Welcome, ladies and gentlemen, to Lesson 7 of Precalculus, which is our Introduction to Rational Functions and is officially called Rational Functions and Their End Behavior. So, let's get started. So, what is a rational function? A rational function is a ratio between a numerator and denominator functions, and for us, those functions are going to be polynomials. We are going to deal with ratio functions made of non-polynomials later on and in calculus, but for our intents and purposes, rational functions are as they are officially defined, which is a ratio of polynomials. They're written in the form of r of x is equal to n of x over d of x, where n of x and d of x are polynomials. So some big ideas to get us started. One is that of domain. So domain is a concept that I will say boggles the mind of a lot of my former students. It took a while for them to really understand what it meant. And we've talked about it before. A domain is all of the possible inputs for a function. This is the first real case that we get inputs that we're not allowed to use. Inputs that can't be considered part of our domain, and therefore we can't use them. So for our intents and purposes, for functions that we define in our class, we're going to assume that their domain is negative infinity to positive infinity, except for three cases, and this is where the first one really comes up. Where we have a rational function, or we have a function that is a ratio, and the denominator cannot be zero. We cannot divide by zero. It breaks the rules of math. So therefore, if we get a function that is ratio, its denominator, when it's zero, is removed from our domain. The next one is an even radical, because if you have an even radical of a negative number, you get imaginary numbers. That's where they come from. And since we deal with the realm of real numbers for domain, we say that we have to have a positive or zero inside of an even radical. A logarithm, which we will talk about in the next unit, super fun. The inside of a logarithm has to be a positive number. It cannot be zero and it cannot be negative. So those are your three major restrictions for right now. There's some trig weirdness later on, but for now, those are our three big ideas, and we're really going to focus on this number one, when we have a ratio, the denominator cannot be zero. All right, so let's find the domain of three rational functions based off of this idea that the denominator cannot equal zero. So when we have a rational function set up like this, it's really easy to see graphically when that's going to happen. We can see that's going to happen right here. So that's going to be negative 4. Analytically, we can see that through, when we can factor at a common factor of 3. We get 3x plus 4. 3 is never 0, but x, when it's negative 4, would make this 0, so x cannot be equal to negative 4. So analytically, we would set the denominator equal to 0 and figure out that way. Graphically, we would look for these asymptotes, these weird behaviors, or we would look for eventually holes. But right now, we're really just going to see them as asymptotes. So sometimes you have to factor. We didn't necessarily have to factor here, but if we look at g here, we do. So we're going to factor this, and that would be 6 and 4. So x minus 6 times x plus 4, because 6 times 4 is 24, and their difference is 2. So that means x cannot be equal to 6 or negative 4. And we can see this graphic, well, actually that's a different graph, so excuse me. So x cannot be equal to those, x cannot be equal to that, and here, graphically, we can see we have an asymptote here. And you just got to do your best with it. Sometimes it's not as easy to write them down, but we have, remember, vertical lines are x equals something, so x equals, or x cannot be equal to negative 2, x cannot be equal to, in this case, 5. So we didn't actually write the domains. We just listed what inputs we can't have. A domain is a list of everything that we can. So for number 1 here, this f here, we would say we want everything but negative 4. So we're going to go negative infinity to negative 4, non-inclusive, and then negative 4, non-inclusive, to infinity. Remember, you can't be inclusive at infinity, so that's why we use parentheses there. For g, we're going to do the same thing. Instead of having 2 parts, we're going to have 3 because we have 2 spots that we can't be equal to. -4 comes first, so we're going to have negative infinity to -4, -4 to +6, and +6 to infinity. The last one has 2 spots that we can't equal, or we can't have in our domain, so it's going to be 3 parts just like the last one was. The first one's going to be -2, so negative infinity to -2, -2 to 5, and then 5 to infinity. So that is finding the domain. Hopefully that's not too awful for us right now, but not too bad. Now let's step into this realm of end behavior. So end behavior, we've talked about it with polynomials, is what in the world are the ends doing as the x values, the inputs, are going towards positive infinity or going towards a negative infinity. So if we look here graphically, we can see that we have this end here, the right end is going up. It's going up slowly, but it's going up, and the left end is going down. So we would use our typical normal we would use our typical polynomial end behavior limits here. So limit as x approaches negative infinity of f of x would be negative infinity for the left, and limit as x approaches positive infinity for the right would be up. So that's not too bad. But rationals don't have to follow polynomial end behavior. They have unique end behavior all on their own. If we look here, this graph has a little bit of weirdness going on. So this graph, f, had end behavior that was going up and down forever, right? But this one doesn't look like it's going up and down forever. H looks like it is getting closer and closer to a number. So what I'm going to do is I'm going to draw a horizontal line at that number, just so we get a better idea. So it looks like on the left, it's getting closer and closer to -2, and on the right, it's getting closer and closer to -2. That's a little weird, but that is our actual end behavior. So for polynomials, they are allowed to approach numbers instead of just infinity or negative infinity. So we are getting closer to -2 on the left, and the right, we are getting closer to -2 as well. So that's a little weird, but it's possible. So for our rational functions, they're going to follow 2 different types of end behavior. We're going to have our infinite end behavior, like we did with polynomials, where they go up and down forever. Or we're going to have this weird end behavior where they approach a number. And for us, they typically should be approaching the same number. We're going to see some weird functions in calculus where they might not. So how do we find it numerically? Numerically means that we are going to plug in numbers and see what we approach. So what I've done is I've gone ahead and plugged them into my own calculator. You should probably pause the video and try plugging in these values and see if you get the same ones from me. But what I got is on the right-hand side. Remember, when we're dealing with positive numbers, we're on the right, and the negative numbers were on the left. But on the right-hand side, I got 0.696, 0.041, 0.004, and then something that rounds to 0 at 10,000. And then I get similarly small numbers, but they're negative over here. 0.427, negative 0.0, oh, that's a 3.4, my bad. 3.4, negative 0.004, and then something that again rounds to 0. So they're below the x-axis on the left, above the x-axis on the right, but it looks like they're getting closer and closer to 0. So we would write limit as g of x, well, as x approaches negative infinity of g of x is equal to 0. Limit as x approaches positive infinity for g of x is also 0. A little bit weird, but again, it approaches a number. And how we can tell? Well, right now, our 2 strategies would be we can graph them and see what happens, or we can find it numerically using a calculator. So what does it mean when we have the left and right sides approaching a number instead of infinity. That's what we're going to define as a horizontal asymptote. So a horizontal asymptote is when the left and or the right end behavior approaches a number instead of infinity. So it doesn't have to be both, it just has to be one for it to be a horizontal asymptote. So what that looks like in limit notation is here in this big idea. So what does this look like analytically? So we're going to find the end behavior of these functions and see what's going on here. We don't have a strategy yet to handle this analytically, so I did it numerically. I don't like the whole chart. I'm just plugging in a really big number and seeing what it's really close to. So what I'm going to do is I'm going to plug in 1,000 and negative 1,000 for all of these functions, and then use that to have a rough idea of what my end behavior is going to be. So f of 1,000, that's not 1,000. F of negative 1,000. So f of 1,000 is 0.002. F of negative 1,000 is negative 0.002. I'm assuming it's getting closer to 0 on both sides. So that's what I'm going to write as my end behavior. The limit as x approaches negative infinity, f of x is approaching 0, and the limit of x approaches positive infinity of f of x is also 0. There's a weird thing there. 0 seems to be quite common. Let's see if we get some other numbers like we got before. Last one was negative 2. So let's see if we get negative 2 again. So let's plug in 1,000 and negative 1,000 for g and see what happens there. Oh, I'm messing up. So g of 1,000 is 199.959. G of negative 1,000 is negative 200.039. So what do we think the end behavior is there? Is it getting closer to a number? No, this one seems to have the infinite end behavior that we had with polynomials. So it looks like the right is going up and the left is going down. So the limit as x approaches negative infinity of g of x is negative infinity, and the limit as x approaches positive infinity for g of x is positive infinity. Weird. Let's do h and see what happens there. So h will do the same thing. We're going to plug in 1,000 and negative 1,000. And h of 1,000 is 2.003, and h of negative 1,000 is 1.997. Those numbers look really close to 2 to me. So the limit of h of x as it gets closer to negative infinity is 2, and the limit as x approaches positive infinity of h of x is also 2. So it looks like we really get 3 major cases. We get 0 sometimes, we get infinite we get the infinite end behavior, and we get the number other than 0. So what seems to be the common denominator here? What seems to be the relationship between these 3 problems and the problems that we covered before? Well, infinite, negative 2, 0. 0, infinite 2. Well, it seems to me when there's a larger degree in the numerator, we get this infinite discontinuity. A larger degree in the denominator, we get 0. And if they're the same, then we get a real number. And in fact, that is our big idea for rational end behavior, is we look at the degrees when we're trying to figure this out analytically. That way we don't have to plug in numbers every single time. Sometimes we don't have calculators for things, or we don't have access to the graph. So we can use the degrees of these functions to figure out what their end behavior is going to be. Remember, not everything is given to you in standard form. So you might have to look for the term with the highest power, or you might have to count the number of zeros in each polynomial if it's in factored form. But if the degree in the numerator is larger, you have no horizontal asymptote. You have that infinite end behavior. If the degree is equal, then you take the leading coefficients of each polynomial and you take the ratio of them. And that is our horizontal asymptote. And if the denominator has a larger degree, then the asymptote is 0. So knowing that, question 5, we are tasked with finding the horizontal asymptote of these rational functions if it has a horizontal asymptote. So to figure this out, we're going to check their degrees. We have a degree 2 in the numerator and a degree 3 in the denominator, which means the denominator's degree is larger. This has a horizontal asymptote at y equals 0. Then in G, we have a degree 2 polynomial in the numerator, degree 1 polynomial in the denominator. So this has no horizontal asymptote because it would have infinite end behavior. And finally, we have a degree 2 numerator and a degree 2 denominator. So we're going to take their leading coefficients and take the ratio of them. There's a 1 here and a 3 there. So y equals 1 over 3 would be our horizontal asymptote. Here's the fun part. We get to come back to limits and we're going to evaluate some limits. So to evaluate these limits, we need to see what the end behavior is going to be. So if you see an infinite limit, a limit being where x is going towards positive or negative infinity, it's asking us what's the end behavior of that side. So this is asking us end behavior of the right. So let's figure out what's going on here. I see 2 zeros in the numerator and a degree 2 in the denominator, which means that we have a degree 2 divided by a degree 2, which means that we're looking at the ratio of the leading coefficients, but I don't know what the leading coefficient is. So we are going to take the x and the x parts of each of those linear factors, and we're going to multiply those. So the leading term of this would be 2x squared. Leading term of the denominator is x squared. Ratio of their coefficients would be positive 2. Now, positive infinity doesn't really matter for us because we know that they're both going towards the same side. The positive and negative infinity for right now doesn't really matter in terms of an asymptote. What it matters is when we have our infinite discontinuities. And later on, we're going to have like exponential functions that have different end behaviors on the left and right side, and that's when it becomes a little bit more important. So if you're getting something like this where you have a horizontal asymptote, it really doesn't matter which side we're looking at. But if we don't get a horizontal asymptote, like we are in the next one, that's where left or right really matters. So in this next one, we have a degree 3 divided by a degree 2, which means we have that infinite end behavior. So we need to figure out what's happening on the left because that's what we care about on this one. So we're looking at the end behavior of the left. So what we need to do is we need to plug in a really big negative number essentially, or a really negative number. I like just throwing in negative infinity because it makes my life a little bit simpler. So we have 3, and we're only going to look at the leading coefficients because they're the ones that really matter. So 3 times negative infinity cubed over negative infinity squared. Well, negative infinity cubed, a negative times a negative is a positive, times a negative is a negative, times 3 is just infinity. So we have negative, some sort of really, really big negative number in the numerator. The denominator, we have a negative number squared. We're going to get a positive, which means that we're going to have a negative number. This is going to go towards negative infinity. So those are your strategies for evaluating limits right now towards infinity, which again just states what is the end behavior here on the right or the left side. Hopefully we're not feeling too overwhelmed. The big idea here is that your end behavior follows one of 3 possibilities. Your degree in the numerator is larger and therefore there's no horizontal asymptote. The degrees are the same, which means that the asymptote is the ratio of the leading coefficients, or the degree of the denominator is larger and therefore the horizontal asymptote is 0. So I hope that one wasn't too bad for you. If it was, make sure that you ask questions in class. Otherwise, I'll see you in the next video.